Hey, everyone. Today we're going to be looking at a graphical approach to these radicals we've been talking a lot about. So there's some new aspects to this, but really everything we've done, we did before in section 2. Now we've taken, as a Math 3 team, on this one, a deeper look at this after we saw what happened with Unit 2, and we made sure that we're not going to run into some of the same issues. So we're not going to be looking at horizontal stretches. Again, horizontal stretches really don't make sense because you can always think of those as a vertical stretch, and that's how, as mathematicians, we always think of those. The only exception to that really is when we're looking at trig functions, where it does really make a difference because we can't translate that in a different way. So we're going to be taking those horizontal stretches out of the equation, and you should only see vertical stretches like we did kind of towards the end of Unit 2. So that being said, we want to go ahead and start off by thinking about what these graphs look like. So let's take a second, let's head over to Desmos, and we're going to graph the different functions. So I'm going to start off with the square root of x, okay, which just looks like that guy. The other ones, we're going to need our calculator here, and I need to hide this. Functions. Here we go. And then I want to do the cube root of x. Okay, and you notice on the square root of x versus the cube root of x, the square root of x only goes in one direction. And that's because I can't take the square root of a negative number. But I can take the cube root of a negative number. That's okay to do. So for our next one, we want to do fourth root of x. So it looks very similar to that square root. And again, we can't take that square root of that, or like fourth root, any even root of a negative number. That's not possible for us to do. And then the fifth root, assuming the pattern holds, oops, sorry, a new one. Assuming the pattern holds, it should look very similar to that cube root, but just a little bit sharper. So again, you get those odd roots that look very similar, and then you get the even roots that also look very similar. If we kept extending that, they would keep looking kind of similar for the sixth root of x. Again, very similar to the fourth root and the square root. It's just it's got a sharper turn. So going back, so our square root looks something like this. Our fourth root, a little bit sharper, and then it caps off a little faster. The cube root has two sides, and then the fifth root looks the same, but again, it's a little shorter and a little sharper turns. Okay, so that being said, we want to look at these transformations, and so we're just looking at square root for a second. We're going to do these really quick and just kind of see how they work and see how they play. So I'm starting out, I'm going to keep my parent function there. I'm going to do +2 and then -2, so we're going to square root of x plus 2. So if you notice, it went to the left. Now, if I think about this and I go back to when we were looking at it, when stuff was inside the parentheses, it gave us that horizontal shift, and it went the opposite direction of what made sense. So when I talk about a positive, it's going in the negative direction, and when I have a negative, it goes in the positive direction. So when I do -2, it should go in the other direction, which it does. Okay, and then when it was outside, like on this one here, remember it moved up and down if it was outside the parentheses. So I've got +2, in this case -2. So that +2 moved it to the left, and then the -2 on the outside moved it down. And remember, outside did exactly what we thought. If it was negative, it went down. If it was positive, it went up. And then this negative out front on the last one should flip it for us, which it does. Okay, and really remember that flip happens first before we move because we want to do it in the right order. So what we see here is that what we think should happen happens. What happened in the unit 2 with all those other functions is still continuing to happen nicely for us. So let's look at now also the domain and range of these functions, though, because the domain and range is what's actually kind of interesting on these functions. Because when I was talking before and I had my cube roots, so my square root of x, right? I can't have any negative x's because as soon as I hit negative, it becomes a negative square root, which I can't have. But for my cube roots and my odd roots, I could. So my domain and range are different depending on if it's an odd root or an even root. If it's an odd root, then it's all real numbers for both the domain and range. There's not a single number I can't put in there and not get a number out. Now, it may be a gross number, but it'll still give me a number. The square root, though, my domain, the x's that I can put in, I can only put in positive x's. Now, my range, though, and if I, kind of zoom out, it's kind of hard to see because, again, and this is one of those things in math that's hard to think about because it's going up and it stops like going up as fast because of how the nature of square roots works. It feels like it's just kind of going to the right really, really, really fast, and it's not really going up, but it is. And if I keep going to the right forever and ever and ever, eventually it's going to hit infinity. So my range here is going to be from 0 all the way up to infinity. Okay, so for the standard parent functions of square root of x, my domain is all x's greater than or equal to 0. My range is all y's greater than or equal to 0. And then for the cube roots, domain is all real numbers, and range is all real numbers. Oh my gosh, sorry. Okay, so when I have an odd root, it's always going to be all real numbers. It doesn't matter where it is. Okay, so for this one, I have an odd root. Let's put that in and see what it looks like, but it should be all real numbers for it. So -3, oops, not -3, -3. Okay, all it did was flip it and stretch it out a little bit, but it's still all real numbers. Okay, so if it's an odd root, it's going to be all real numbers for both the domain and range. If it's an even root, I need to be careful on where it's really starting. Okay, so these are those translations again. And again, we are not going to worry about a horizontal stretch or shrink. We're going to avoid that length of plank because really I could take that out and make it a vertical stretch or shrink. But we're not even going to do that portion of it. Okay, but remember that horizontal means it's on the inside, like here. The vertical translations are on the outside. Reflections are on the inside or on the inside of the outside, and those are those negatives. And then stretches and shrinks. Again, we're just going to worry about the outside. We're not going to worry about ones on the inside. So that being said, let's look at this one here. So I started off with a parent function of f of x being the square root of x. I've got a horizontal shift or translation. Okay, now again, it's on the inside, so let's go to the opposite. Usually negative, we think going to the left, but now it's going to go to the right. So it's going to go right 3, and then a vertical, this 4 outside, shift, and it does what we want to because it's outside, up by 4. Okay, so thinking about our parent function looks like this. So it's going to move to the right by 3. And now you always want to move like kind of the middle point. So it's like there. And then it's going to go up by 4. So it's going to be up here. Okay, so my domain and range of this one is all my x's from 3 or bigger work, and then all my y's from 4 or bigger work. So my domain here is going to be x greater than or equal to 3, which makes sense because I can plug in 3 here, right? 3 minus 3 gives me that 0. But if it was 2, right? 2 minus 3 is now a negative, and I can't have a negative square root in the real plane. Range is going to be y greater than or equal to 4. It's never going to be less than 4. It's going to start here, and it's going to go up, and it's going to keep going up. Slowly, but it's going to keep going up forever. Okay, so same idea. Graphing this one. This is my parent function. Now for this one, I am going to move to the left by 1. So instead of starting at 0, 0, it's going to start at negative 1, 0. So my domain is going to be all x's greater than or equal to negative 1. My range is going to be all the y's 0 or greater. Okay, for this next one, I want to do this flip first, so it flips over y, or sorry, over x, not y, x is on the outside, and then it moves down 2. Okay, remember a cube root looks something like, oops, draw that a little better, something like this. So when it flips, it's going to look something like this, and then it's going to move down 2. And again, we want to move that middle point. That's the best point to move. So it's going to look something like this, down by 2. So it's going to go through here and then come down. Let me make that blue so it's a little easier to see what's going on. It's going to look something like this. Okay, for these ones, and this is where it gets a little tricky, because if we have Desmos, it's actually not too bad. But if we don't have Desmos, this is where we got to be careful, especially if you're using like an 83 or an 84. So on this one, let's just put it in just like it is and see what happens. Okay, because if I think about this one for a second, it kind of feels like it should be a parabola, and it tells us, hey, there is a vertex, there is a parabola, but which direction is this thing going is going to be the problem for us. So let's type it in and see what happens for us. So I have 1/2 y squared equals x. Okay. Now in Desmos, again, this worked really nicely for us. Let me zoom back in a little bit. In Desmos, this works really nicely for us because Desmos knows how to play with those y squareds. Unfortunately, in an 83, I can pull mine up real quick. Excuse me. Unfortunately, in an 83, there's no way to turn this y into a y squared. So I need to think, okay, well, how can I get that y squared to just a y? And that's the goal here, okay? So again, in Desmos, really nice, just plug it in. But again, I wanted to make sure you're ready for ACT or SAT on this. So the idea is we want to get y by itself, and we want it to not just be y or y squared, but we want it to be just y. So I'm going to multiply both sides here. Let me rewrite this. Y squared equals x. I'm going to multiply both sides by 2 to get rid of that 1/2. This cancels. Put this in the right order. We're going to say 2x. Now, at this point, to get rid of that squared, we need to take the square root. Okay, but if I plug that into the calculator, and again, this cancels, which is nice for me. But if I plug that into the calculator, what's going to happen is, second, square root 2x, close parentheses, graph that. See, it's not the same as the one we got on Desmos. And the reason is because we forced a square root. We are the ones who took the square root. Okay? it was not given to us. If it was given to us like this, the problem said, okay, we've got this. This is our function. Yay, done. Then we don't need to do this. But because we took the square root, we forced that square root, we needed to do the plus minus. Now, again, there's no way to do that in the calculator. So what I'm going to do is I've got my plus, and I'm just going to do a minus version of that. 2x, close parentheses, and now it gives me that other side. And we can throw this into Desmos and look at it too, just to make sure it worked nicely for us. So y equals the square root of 2x. So there's that top side. Y equals the negative square root of 2x. And then that gives me that bottom side. Okay, so again, this was the original, which Desmos does do for us. And here's the one that we would split up. So again, if you're using a calculator, that's fine. And it's good to know how to use the calculator for, again, ACT or SAT. But Desmos does just kind of do it for you if you're not quite worried about that quite yet. So I've got a problem here, though. So when I think about this, my parabola opens to the right. My vertex, let me get rid of these two so I can see that. My vertex is at 0, 0, which is fine. Like I can make a graph like this, but the problem is it's not really a function. These two, this is a function. And this is a function because it passes that horizontal line or that vertical line test. Remember, if you drop a line anywhere on that function, as long as it only touches it once, at most once, because it definitely doesn't touch it once over here, and that's fine. But it touches it once here, and that's okay, okay, okay. But if I go back to that first one, the only spot it touches it once is at the vertex. Any other spot, it's touching it twice. So this is not technically a function. So that is something we do have to think about and think about too. So again, graphing calculator. If we're using Desmos, this is going to work really nicely for us. If we're not, we're going to need some tricks. So doing it in Desmos first, x squared plus y squared equals 16. Okay, again, works really nice for us. We can see that the center is going to be at 0, 0. And if I wasn't sure of that, I could look at some of these points on the outside, right? And go, okay, well, the middle of these 2 points is 0s on the y's, and the middle of these 2 points is 0 on the x's. Okay, but again, calculator's not going to do that nicely for us. So what we need to do is we need to get y by itself. So x squared plus y squared, 16, minus x squared, minus x squared. So y squared equals negative x squared plus 16. Square root. Okay, now I forced that square root, so I need to do plus minus. So y is equal to plus minus negative x squared plus 16. Okay, throw that in my calculator. Oops. Come on, yeah. Okay, so I'm going to do the square root of negative x squared plus 16. And let's go ahead and just do the negative at the same time. Negative x squared plus 16. Graph that. Okay, and now it doesn't look like a circle, which kind of freaks people out sometimes, and we get this gap here. So that gap there is just a rounding error in the calculator, but this is, those would connect. Now, if I wanted it to look more circle-like, what I would do is I would go down to z square. And we can see it's a little more circle-like now. Okay, so what I can do, though, is I can do trace. And if I want to go over and look at like 4, okay, you can see that it does, in fact, go down to that point. Okay, so it's a rounding error in the calculator that makes it look like it doesn't connect, but it does. Okay, this one would be the same thing. Okay, using that, identifying where that vertex is, same idea. Where's the radius? What is the intercepts? Again, that's just going to Desmos and letting it do the work for you. And then graphing this one. Okay, I want to deal with this stretch first. So this was my original. So my stretch is going to look something like this. I'm going to move to the right by 1. And then I'm going to move up by 3. And I always want to move, oops, 1, 2, 3. You always want to move the point where it kind of starts. So it looks something like this. Okay, that's it. So the big ones to watch out for are the circle ones. But again, Desmos does those really nicely for you. And since you can use Desmos, I would definitely use it. If you want to get that practice on the calculator, though, feel free to do that. If you're getting stuck, make sure you're showing up for RTI time or before and after school tutoring. And that's it. And I will see you guys next time.